Hi. All right, let's get started. So this is tests versus types. We're going to explore some good things and bad things about tests, types, and how they work together. So first, who am I? I'm awkwardly waving. I'm senior software engineer at Rubicon Project. I work mainly in data pipeline or big data, as the buzzword might, if I was using buzzwords. So yeah, we work on automating the buying and selling of ads on the internet. We have huge piles of data that we work with. If you're interested in talking about that, we're always looking for good people, so come find me. We can talk further. I'm always looking to make software more correct, easier to test, easier to use, because we're in the place where we want to write software really fast because we feel like we have to get it done, but then the people who read it for years and years afterwards suffer because we had to get it done. So first of all, what are types? In general, this is the joke image about, hey, you know, I'm playing Swords, or I'm playing foosball, or I'm reading Reddit, because I'm compiling. That takes a long time, which can be true. Like if you have a very large project and you're compiling using a slow compiler or a powerful compiler, it might take a long time. You can mitigate some of that through separating your projects and things like that, but really it does take time. So there are crappy types. There are type systems that are bad. And these are the types of things we're exposed to in CS 160, CS 220. Like as we go through, we learn about Java. And we learn about, okay, when I create a data object, I have to declare equals that takes object. Well, why does it take object? An apple's probably not equal to an orange or equal to an integer. And if it is, wow, if that's your universal equality, then you're probably in a bad place. Or the second one where you're, okay, I said it was a list, a map, a string of objects, and then I had to say again, list, a map, a string of objects. Like typing these things over and over and over again. And it gets really painful, and it takes a lot of our time, and we kind of get disenfranchised with the idea of type systems because we say, well, in JavaScript, I just have to type a list, and it just works, and I don't have to worry about what type it is. It just works. And then the last one is okay, I want this list to have a very specific type. I want it to be either integers or doubles, whatever I'm adding to it. And Java's nope, you can't do that. Collections are invariant, and that's just the way it's going to be. Now, variance with mutable collections is a bad idea in general, but we won't dive too deeply into that. Or this. This is, last night I was I wonder what IntelliJ would do if I told it to generate me a class that was a person class that had first name and last name. And I intentionally made it small because I can't make it big and fit all the code on there. So all this is just a data object that represents two strings in Java as getters and setters. But it generated equals, it generated hash code, because you have to have these things for this to work correctly. So it's no wonder that we come out of school or run into things like this, and we're I don't even know what's important in this class. I just can't tell you anything that's important here. It would take me a long time. It's super frustrating to me because people get frustrated with type systems. They're like, this is too verbose, I don't like it. And they just head and hands walk away. And they walk away to stuff like this, to Python. Python is a great interpreted, dynamically typed language, and sometimes Python is the right tool for the job. But in this case, I was like, okay, well, I want to get out the value that's at index 1. Well, it turns out that's not what the index function does, but Python doesn't tell me that. It says, no, I couldn't find 1 in the list. Well, of course you couldn't find 1 in the list. It's a list of strings. There can't be a 1 in the list. You knew that you knew it was a list of strings when you ran this code. Why didn't you tell me that instead of telling me, oh, 1's just not there, it's fine. Or things like this. Drives me crazy knowing. It knows that X is hello. It says here right in the error message, it says unsupported operand for int and string. It literally knows the type. And yet, instead of giving me an error that says, hey, these two types don't match, or you can't do this, it's just like, well, you can't add int and string. It doesn't say these two types don't match. So types are just labels. They're labels that a program assigns to your program to help you. They're not like super verbose things that are super constricting. They're not ugly and long. They are just labels that can be assigned by very, very powerful compilers or very, very simple compilers. The C compiler is very, very simple in terms of how it assigns the labels. It'll let you do anything. If you want to hear horror stories, you can just go talk to Bob and he will rant about C. But we don't need to be disenfranchised by types just because we ran into bad type systems. So, what are good type systems? What allows us to have the power that we want without giving up the flexibility we want? We would like to have our cake and eat it too. That would have been a good game. So implicit. You don't want a type system to enforce you to explicitly state the type all the time. You want to be able to do what JavaScript does and say var x equals food. Like, you want to be able to do that, and you should be able to do that. Like, that is a completely reasonable thing, and type systems can handle that. Good type systems. Terse. Like, you don't want to say the type a few times. Even if you want to put a type declaration on something, you don't want to have to say it more than once. That's just insane. Like, what? Why should I need to say things more than once? Prototyping. A lot of times when we're trying to write under-defined code, we only want to write the happy path. We don't want to write the unhappy path. We don't want to write, the stuff that is hard to write that talks to the file system or whatever. We just want to put in like, I'll worry about that later. Your type system should be able to allow you to do that. Self-documenting. If you're going to use a type system, it should at least give you documentation that tells you what these things do. And that documentation will always be up to date because it's checked by the compiler. But that's an important thing. And it should be easy for people to read. It shouldn't be Java where there's 50 lines and I can't tell that it's just a data type that has two strings in it. So, implicit. So I took 3 examples here. I'm going to use mostly Haskell and Scala as my good type system. Note that Scala has a bunch of the words that Java has if you just allow willy-nilly anything in your code base. You can restrict it to what they call the safe set of Scala, which gets it closer to more of a pure functional language. If you do that, you can leverage a lot of power that you have in a type system like Haskell. But so here, this is just the REPL for all of the languages. I say val x equals 1. So it's implicit. It's just said, oh, I implicitly found out that's an integer. I will happily say it's an integer. Everything's good. That's great. I didn't have to say integer x equals new integer paren 1 paren, which to be fair in Java you wouldn't have to do that either. But the second one is Haskell, and Haskell you use at least on the REPL let to declare a variable, and I'm saying let x equals 100, and then that $tx is just me asking the REPL, give me the type x. So in this case, Haskell was even more loosey-goosey than Scala was. It says it's some type A that is a numeric. It's not even restricting to integer. It's just numeric. And if I needed something to be, if it needed to be a float later, it would just be okay, it's fine. We got you covered because it could bind the type correctly at that point. And then this last one is add 1. I'm declaring a function add 1 that takes an x and just adds 1 to it. And again, I asked the Haskell what the type of that is, and it says, again, it's just a type A that is numeric. So Now I can call it with an integer, I can call it with a float, I can call it with anything that was numeric. I didn't have to write that multiple times, I didn't have to tell it was a type, it just worked it out. Okay? So that's what I mean by implicit. It's working things out for me that I don't need to say. Terse. Man, terse code is just so much easier to comprehend. Even if it's dense, it's at least only, one line instead of 50. So here, like, the add one function is very terse. It's just saying add, basically you can say it as just +1, which is a very interesting feature of Haskell, but we won't dive into that. Or creating new data types. So this here is declaring a data type that is either nothing or just that holds some type A. And so this is probably, well, first of all, you can't even write this in Java because this is what's called an algebraic data type, which Java does not support. But if you did, you would still have to write equals. You have to write hash code. You have to write all these things for it, which you don't have to do here. Or declaring enum that is just super concise. It's all in one line. That's just an enum that says, hey, day is one of these things. So, and then just to poke one more time in Java, that last one is exactly the same as the 50 lines of Java that we wrote before, because Scala generates you hash code, generates you equals, generates all these things that you need, but you shouldn't have to write. So those are all terse. Okay, prototyping. We talked about the fact that when you're writing code and you're trying to prototype, and trying to create things quickly, you don't want to spend a lot of time doing stuff that you don't need right now. So your type system should support things like this. This first line that has the triple question mark at the end, that's me telling Scala, I'll worry about this later. It's fine. Just work it out. I promise, I'll deal with it later. And Scala will compile that, and we'll just say, okay, everything's hunky-dory. You're fine here, but if you call it, it'll throw an exception. It'll say, like, unimplemented. But at least, as long as you're testing a different path, you don't have to worry about it. You can just say, okay, I'm going to write that thing that goes and lists all the files in a directory later. And for now, I'm just going to pass it a path that has that isn't a directory, and then everything will just keep working. And the same thing here below in Haskell, where like the undefined here is essentially like the triple question mark, which is telling the type system, no, just trust me, I'll get back to that. So you can iterate very quickly without having any compilation problems. So self-documenting. So we talked about like implicit and terse, and these things are both really good. But when it comes down to documenting your code, I don't know if people are like me that you write a bunch of code and then you're like, oh man, I really should put some comments on this. So you're kind of going back and working through this, and instead of putting a comment on this thing that says, oh, this returns a list of paths, I can just put the type annotation on the end there, this list path, which now, okay, this documents the fact that this takes a path and returns a list path. I get documentation for free. Well, free, I had to type it once, but the compiler will always keep it in check. If somebody messes up this function, there's no possibility that that comment gets out of date. It's checked by the compiler, it's verified, it's going to be correct. So all I did here was basically just put the two type annotations on the end, which I find myself a lot of times writing comments like, well, this returns a list of paths. Like, well, why am I typing that? The type says that it returns a list of paths. I should be either saying why it returns a list of paths or some other piece of information as my comment. It should not be like just telling you again what is already obvious. And then this is roughly the version of index that we were looking at from Python, where instead it takes, so it's basically saying for any type that you can compare, that just says for any type A that you can compare the elements, because in Haskell you don't have universal equality, so you have to know that you can compare something before it will compile. And it says, so give me one of those elements and a list of those elements, and I might give you back the integer where it was found. So now immediately I can tell, okay, so I'll give it an element, and I'll give it a list of elements, and oh, it might return nothing. It might not be able to find that. It's immediately obvious from the type signature that it's possible to not find an element, which in both Python and like Java, they just be like, oh, we return null in this case, or we return -1. Like that's my favorite. Return an integer, but not an integer that means anything useful to you. So if I try to compile this, where I look for 1 in this list, it's going to just not compile. It's going to say, don't, like, you asked for strings, there's strings here, and there's an integer, like, I can't make these things work, so it's keeping me from hurting myself. But these work great. Like, if I ask for foo, it gives me just 0, which is what I would expect, or nothing if it couldn't find one. So now the type has made it completely obvious that what the failure condition is even. So now I know that if it doesn't find something, it's not going to throw an exception. It's not going to return me -1. It's going to return me this maybe type. Okay, so I'm done ranting about type systems. Let's talk about what types versus tests and how those two things come together. Okay, so we're going to write that function we've been talking about. Well, or at least the type signatures for it. So given a list and a value, return the index of the value in the list or signify that it's not found. So I chose, there's a blog post out there where a guy did something similar to this, but he did a lot more languages and it's really long. So I condensed it down here. But these are the metrics like I'm looking to measure. So documentation, we want to see example usage, like how is this function supposed to be called? Some legal values, does it handle some legal values? Does it handle all the legal values? Specification, it works for one case for. The really crazy nice thing to have would be, I know that the return value from this function is valid. That would be a super useful thing. Common errors, like I didn't make a typo, there's no unexpected null. I'm forcing the caller to deal with failure. In a language like Python where you don't have types, you can't force the caller to deal with anything. The caller doesn't have to do anything. They can do anything they want. So that's something I want to like force onto my callers to have them deal with that. Guarantees. So they're forced to call things with correct type. No side effects, just meaning the function does exactly what it says it does. It doesn't like go out and launch the missiles or whatever. It doesn't throw exceptions, and there's no infinite loops. So these are all metrics. So the contenders. We'll look at Python, and we'll add tests to that. Haskell with type annotations and with type annotations and tests. And a language called Idris, which if you've never heard of it, is a dependently typed language, which we'll talk about when we get there. But it's really interesting, but slightly academic. Okay, Python without tests. So we're basing purely on what the definition of the function says and the types say about it, or the tests say about it, and not what like you can write in a comment above it that's not checked. Not looking at the implementation and reading it and trying to understand it. So I mean, Python basically tells us, right? It's a function that takes two things. That's what we know. We don't know what it does. We don't know how it does it. We can't tell anything based on just looking at the type signature. Which, I mean, to be fair, that's exactly their design goal. So you add tests. Now you get, okay, now we have example usage. We know how this thing works. It says, okay, you pass find, you pass a list to it, you pass something else to it, and it gives you back the index. Or you pass list to it, pass something that's not in the list, and it gives you back none. It says, nope, didn't find anything. So now we know that it works for one case. We know it works for some amount of legal values. We can't really tell if it works for all, but we know that it at least kind of works. So now let's flip over. In Haskell, the same type of thing, we get a bunch of guarantees out of the gate from the compiler. We get guarantees that there's no typos because it wouldn't have compiled if there was. We know there's no null. Well, Haskell doesn't have null, so that's kind of cheating. But we force the caller to deal with failures because, again, it's type checked. So if the caller didn't deal with the failure, it wouldn't compile. Has to be called with the correct type, again, compiled. And no side effects because the function says it doesn't do any side effects. And in Haskell, like, unless your function says it does side effects, it doesn't do side effects. So you get a completely different set of guarantees from types. People often argue, well, if you have types, you don't need tests. Well, that's not true, right? We don't have example usage. We don't know that it works for some legal values. We don't know if it works at all. I mean, we're saying it compiles, but that doesn't mean anything. So these two things are orthogonal to each other. They're not parallel in any way. They don't do the same thing. All right, so if we add type annotations here, we can say, again, for two things that can be compared, that's all this EQA says. It says, so for some type A that can be compared, that has a quality, a list of those A's and a value of type A, I'm giving you back maybe int. Okay, so now we know that it can handle the values of a list, and it can handle the values of for any type A that can be compared. Now, I am ignoring the fact that you might have put an undefined in there, as we were talking about earlier with prototyping, which is kind of cheating because you can lie to the compiler and tell it, trust me. But I mean, assuming that you actually wrote code and you didn't put an undefined in there, you're in the place where it works. And obviously, you still have all the guarantees that you had before. Okay, so now if you add tests, so these are just two tests. One that says it's going to get back just 0, which is representing the 0 element, or nothing if the value wasn't in the list. So I just wrote two test cases, and now we have example usage, and we've gained all the things that we gained from Python writing tests. So now we have nice example usage. We know it handles all the cases. We know that it for sure works for one case because we've tested the happy case and we tested a sad case. An aside here, a lot of languages nowadays have libraries Quick Check or Scala Check. These are example libraries that generate you random test cases. If you're interested in that kind of thing, it can be really powerful. If you can write random generated test cases, it can catch a lot of defects. All right, Idris. So Idris is, like I said, a dependently typed language, which what that means is that types depend on the values. So you've got this language, you've got a weird relationship that you don't normally get in a programming language, where if I pass you a vector, so this is a vector of length n that has values in it of type A, when this function is invoked, it knows at runtime or at compile time what the n is going to be. So because it knows what n is going to be, you can get a lot better checking on your return values. So what this says is fin n just says that value that it comes out of here is going to be between 0 and n. Gotten to the place where you could say, no, this return value is for sure valid, but you can say it's at least in the range. Like you would not, using that index, if you indexed into that vector, you'd be guaranteed not to get an out of bounds exception or any kind of error like that. So it's a completely different way of thinking, and it hurts my head a lot when I try. But it is something that's interesting to look at if you're interested in type systems or interested in making the compiler try to do all of the work for you. So there's also this % default total. Idris supports totality checking. So that is to say, I can guarantee you that this function halts. Now, Bob Wall back there, he's thinking, halting problem, that's not a thing. Sorry, you're not solving that. The way that they get around that is it's only on functions that operate on specific types, and they don't support general recursion. Like you have to be like taking and shrinking your data in some way, taking the head off of a list, or there are some rules that come with totality checking that keep it away from the general halting problem. But it's neat, but it also hurts my brain. Okay, so now down here to what we actually get out of this. We actually get quite a bit. We don't get example usage. We don't know that it actually works for one case, or that the return value is valid. We do know it's in the range, but we don't actually know it's valid. But again, we get the no exceptions, no infinite loops, no side effects, all from the fact that the language just doesn't support that unless it's in the return type of function. Okay, so this is as far down the rabbit hole as I'm going to make you go. But in Idris, when you write a test, you essentially instead just tell it the type of the expression is a particular value, which is a very strange way to think. Because now you've just taken and said, instead of this expression looks exactly like a test, right? Find foo bar is 1. That looks like a test. It's a type on the expression. And then you could just say to Idris, REFL, which just means try to resolve that and see if it's true. And it does it. Now, I won't claim to be an expert in Idris, and I don't really want to be. I mean, it's an interesting thing to learn, and it's interesting to dabble in. But if you really want to learn this stuff, there are some very smart people who are researching it and providing good books. He's writing a book right now. But we didn't quite get all the way to return value is valid. We don't know for sure that the value that came out of there is valid. You can take Idris one step further, which I'm not going to do, and tell it to literally prove that the implementation is correct using the type system. Again, you're not going to probably write software for your day job in Idris or anything like that, but it is interesting to know it exists, and it can be kind of fun. Okay, so this is what I should have just shown you and then walked out of the room. This is like what you get in the different languages and from the different type systems. So I think the most interesting thing, at least to me, is that, like we talked about earlier, there's just the idea that you can either ignore tests if you have a type system, or that you don't need a type system if you have tests. Those two things are just not the same. They're not providing you the same guarantees at all. Like, if we look at Python's tests, it's providing example usage, some information about legal values, and the fact that it works for one case. Like, even Haskell, which is probably one of the best type systems in like a mainstream language, doesn't provide you those guarantees. Like, you can't just say, I'm writing Haskell, I don't need tests. That's not a thing. If you want to have a good API and you want to inform your users about how to use it, about whether or not it actually works, you still have to have tests. And if you're writing Python, you can't just say, well, once I have tests, I just have everything. I did it just as well as what you would do in a compiled language. It's like, well, no, you definitely didn't. You don't get like, oh, there's no typos. There could be typos all over the place. Python's just fun. Or JavaScript, or take your dynamic language of choice. Like dealing with failure, forced to being called with like a correct type. You don't get any of these checks until you hit the code or your customer hits the code. And so I think with the advancement of type systems and the fact that computers are getting so much faster and people are finding ways to make compilers faster, I think it's worth taking a look at, even if you're like, oh man, I hate when type systems slow me down, right? Java is just the worst, or whatever your exposure. Take some time, look around, and see what you can find that might give you slightly more guarantees. I would like it if you didn't throw things at me now, but I will take any questions or comments or disagreements, as long as you're not throwing fruit or cereal. Good.
So yeah, I was just gonna, since you said we can disagree.
Sure.
I was just gonna say, on your initial Haskell implementation, I think you marked, the color deals with failure. But I mean, there's nothing in there that would, you're not declaring that it returns a maybe. So
Okay, yeah.
There's nothing to prevent you from returning -1, right?
Yep, so you're right. The assertion was that there is actually an implementation there. But you're right. You're right.
Like a good Haskell programmer would return a maybe. But you could write bad.
Yep,
Haskell
you could.
function here.
Yeah, so you're right. That's not as guaranteed, and maybe I should have included it until I included the annotation. But yeah, you're correct that the reason that I included it was assuming that the function was written correctly. You are forcing the person upstream to call it or to deal with that maybe, even if they didn't want to. Like they have to do it. They have to do something with it. But you're right. They could have just returned -1. So I should have probably bumped that to the next slide. Sure.
I'm a little confused with the context of some of this. When you say a test, are these? I'm not familiar with any languages that put that as part of your implementation. Almost is what you're saying.
No, I didn't. When I said that these were the tests, these would be in a test file, like in your project.
Oh, so this is I'm calling the function with this here.
Right. Sorry.
Not as at the same place where the function is defined.
Correct.
Okay.
I was trying to provide short,
All right.
code examples.
So, it was my own confusion there.
No, I should probably been a little more clear about that. They would be defined like in. I'm just saying if you had a Python file that was your implementation, then you had a test suite that you're running against that implementation. That's what I'm talking about.
And you're just putting them on the same slide, basically.
Well, I'm just putting them bare because I don't want to deal with all the stuff that you have to have around it. I just felt like it was a little bit of
Okay.
I'm going to make fun of you though for calling that documentation.
Because
if I have to go into your test directory and dig down to find it, I'm not going to be predisposed to like you.
I do agree with you. I do agree with you. I do want to say that without that test, there is zero documentation. Like you're at least here. Like I've dug through source code where I'm like, just show me. I'm digging through the test suite. I'm trying to find anywhere where this thing is just used. I just want to know how to use it. And I agree with you. You should expose your users to that. But at least the next developer that comes along, if you're working on this project, we do we write code once and we read it for 10 years. Like at least the next developer can come in here and be like, oh, that's what they expected? That's kind of weird. Why did they expect that? And there might be confusion about why they expected something, but at least it's there. Any other confusion or anger? Rotten fruit of any sort?
I had a $50 bill I was going to throw you, but
I'll take that. Take that.
So I mean, just as kind of a sense making, you're basically saying what does literally just the function definition and your test case, what does that tell you about the correctness of it?
Right. I mean, I'm basically just given.
Not even given the implementation. Just
Because
the signature, basically.
we don't want to be in the place where. In order to understand what something does, I have to read 100 lines of, it could be very complex Python. If you have a very complex algorithm, there's a possibility. I mean, this example is easy to understand. Like anybody could probably read it as long as you know the language, and you could get to the bottom of what this does. But if you have something that is very complex, or a series of things which is very complex, trying to figure that out in a language like Python, this last fall I went through these Python code bases trying to figure out just what things do, and like, I don't know. I don't know what this does. This calls this function. Where's this function defined? Like, I don't even know. I'm searching through things. I'm just repping, and like, I don't have any idea what anything does because there's just no types to lead me to a place. Or if I change it, oh god, like I have no idea if it works. I don't even know how to get to this code path. To test it. It gets really, really hard. And even once I can get to that code path, then I find out I made a typo. Oops. All right, try again. And so I become more and more frustrated beyond what I want to endure.
You said one of the guarantees that good function needs to display here is no exceptions. Why would you say that's a good guarantee? Because there's a lot of times in production systems where exceptions tell you a lot of useful things about what just happened.
So exceptions are or can be, well, error messages can be useful. Exceptions that are just being thrown because that's not a good way to write a system. You wouldn't want to use an exception that said, I couldn't find that value here, because then you're using exceptions for flow control, which is one of the huge no-nos.
Right, I agree with that statement.
So, I'm talking about in the context of this function, there should be no exceptions. I agree with you that like stack traces are very useful in production systems, but I would not agree that like things way down at the bottom should be throwing those exceptions. I would say you should give error messages back up, and then at some point, if you can't deal with the system anymore, if it literally like everything has gone so pear-shaped, I cannot continue. Like, all right, throw an exception, like take the system down, log it, all that stuff. But that's not a good way to use like functions way down deep in your system. Should never be doing that. You should be bubbling up those errors and dealing with the exceptional case at the last moment.
And I mean, part of this is like, you want a build time error rather than a runtime error, right? I mean, I think the assumptions with like Haskell is a lot of things that would be runtime errors. You get an exception for the compiler.
Well, I'm getting, again, like at what level is your exception? I was dealing with a system that for a while it was a legacy system. Oracle Forms used exceptions for flow control almost 100% of the time. Every time an exception was thrown, it was used for flow control. When we throw this exception, do all this other stuff, it was used as logic.
How did that make
And
you
that's
feel?
what you're saying.
How did that make you feel?
This was bad. I hated it. It was like we should not even be supporting this anymore. I did not like that.
Right. So in general, in languages that have better types and better type systems, instead of representing that as an exception, you would represent that as like an either type that either holds an error or has a good value. And dealing with those types is very easy in languages that have support for it, like Scala or Haskell. And this type of design philosophy, like we don't need to get into that here, is more of a functional programming type design philosophy instead of like object oriented, where you have a bunch of mutable state inside of an object and you're mutating it, and then like, you got to an illegal state and you just throw. Like that, it's an entirely different design philosophy, which I would trying my best not to get into by just limiting to one function. Any other questions or? Andrew?